What is microservices architecture and why has it taken over the industry? In this video, we are going to break it down from first principles, starting with the problem it solves, walking through every major pattern, and ending with an honest look at the trade-offs. Whether you are designing your first production system or trying to figure out if microservices are right for your team, this is exactly what you need. Imagine you are building an e-commerce platform. You start with a single code base, one repository, one database, one deployable unit. This is a monolith, and at the beginning it is fast and simple. But as the company grows, so does the code base. Teams start stepping on each other's changes. A bug in the payments code can crash the entire site. Deploying a change to the search feature requires redeploying everything, including the parts that had nothing to do with search. Microservices architecture is the answer to this specific problem. Instead of one large application, you split it into small, independent services, each responsible for a single business capability, each deployable on its own, each owning its own data. How do you actually split a monolith into services? There are three common strategies. The first is decomposition by business domain. You group code around business capabilities, so you get an order service, a user service, a payment service, a notification service. Teams own full vertical slices of the product. Second strategy is decomposition by data. Each service owns its own database schema, with no shared tables. This enforces loose coupling at the storage layer. The third strategy follows Conway's law. Your system architecture will mirror your organizational structure. Small autonomous two-pizza teams naturally produce small autonomous services. The strangler fig pattern is the safest migration path. You route traffic to new services incrementally, while the old monolith still runs alongside them. No big bang rewrite required. Once you have multiple services, they need to talk to each other. There are two fundamental approaches. Synchronous communication means one service calls another and waits for the response, typically over HTTP or gRPC. It is simple and easy to reason about, but it creates tight coupling in the request chain. If the payment service is slow, the order service blocks, and every caller of the order service stacks up behind it. Asynchronous communication solves this by introducing a message bus Kafka SQS RabbitMQ. The order service publishes an order placed event and immediately moves on. The email service, the inventory service, and the analytics service all consume that event independently. They are fully decoupled. The rule of thumb: use synchronous for reads where the user needs an immediate answer, use asynchronous for writes and workflows that can be processed in the background. When you have 30 services, how does the outside world talk to them? The answer is an API gateway, a single entry point that sits in front of all your services. The gateway handles authentication and JWT verification so individual services do not have to. It enforces rate limits to protect your infrastructure. It routes requests to the correct service based on the path or headers. It can cache responses and terminate TLS. Without a gateway, every mobile client and every partner integration needs to know the address of every service, and that coupling makes your system extremely brittle. Common implementations include AWS API Gateway, Kong, NGINX, and Traefik. Every production microservices system has one. The hardest part of microservices is data. Golden rule is database per service. Each service owns its schema, and no other service can query it directly. This is what gives you independent deployability and the freedom to use the right database technology for each problem. But it creates a new challenge. How do you handle a transaction that spans multiple services? If you are placing an order, you need to reserve inventory, charge the card, and send a confirmation atomically. The SAGA pattern solves this. Each step publishes an event on success, and if a later step fails, compensating transactions roll back the earlier ones. You also have to embrace eventual consistency. The order might appear as processing for a few hundred milliseconds before all events have propagated. Design your interfaces to handle these intermediate states gracefully. In a distributed system, things will fail. The circuit breaker pattern is the most important tool for containing those failures. The circuit breaker wraps calls to a downstream service and tracks the failure rate. When failures exceed a threshold, the breaker opens and immediately rejects all requests, failing fast instead of stacking up threads waiting for a service that is clearly down. After a timeout, it enters a half-open state and lets through one probe request. If that succeeds, the circuit closes and normal traffic resumes. Alongside circuit breakers, every outbound call needs a timeout, no exceptions. Threads blocked indefinitely cascade into thread pool exhaustion. Retry failed requests with exponential backoff, but cap the retries to avoid amplifying load on a struggling service. The bulkhead pattern isolates thread pools per dependency so a slow service cannot starve all the others. In a monolith, you call a function. In microservices, you call a network address. But what is that address, and which of the three instances running behind it should you use? Service discovery solves this. Each service instance registers itself with a service registry, console, Eureka, or in Kubernetes simply the internal DNS. The registry runs health checks every few seconds and removes dead instances automatically. When the API gateway or another service needs to call the order service, it queries the registry, gets back a list of healthy instances, and picks one. With client-side load balancing, the caller makes that choice itself. With server-side load balancing, a dedicated load balancer makes it. Kubernetes makes most of this invisible. Services get a stable DNS name and the platform handles instance routing automatically. The monolith debugging means reading a log file. In microservices, a single user request might touch 15 services. You need three things working together. Logs give you structured events from each service. Use JSON, include a trace identifier in every log line, and centralize them in Elasticsearch or Loki. Metrics give you numeric measurements over time, request rate, error rate, latency percentiles. Prometheus and Grafana are the standard stack. Alert on your service-level objectives before users notice. Traces give you the end-to-end journey of a request across services. Jaeger and Zipkin propagate a trace identifier through HTTP headers and reconstruct the call graph. When something goes wrong, traces tell you exactly which service in a chain is slow. Without all three pillars, you are flying blind. Instrument from day one, retrofitting observability into 50 services is an enormous undertaking. Microservices are not free. The benefits are real: independent deployability, targeted scaling, fault isolation, technology flexibility, and smaller codebases that individual teams can fully own and understand. But the costs are real too. You are now building a distributed system, which means network failures, partial outages, and latency in every service-to-service call. You need robust DevOps tooling, containers, CI/CD pipelines, service mesh, centralized monitoring. Data consistency across services requires careful design. Integration testing becomes harder when you need 15 services running locally. So when should you choose microservices? When your team has grown beyond 8 or 10 engineers, when different components genuinely need different scaling profiles, and when you already have the DevOps maturity to operate them. If you are an early-stage startup, start with a well-structured monolith. Extract services when the pain of coordination actually outweighs the cost of distribution. Thanks for watching.